our main goal, and the entire reason we're using Rudin et al. This quarter, is that we want to get to these two theorems. These IFT represent the inverse function theorem and the implicit function theorem. So we want to get here. And I don't know if this picture makes any sense, but I drew it. So we're on this road and we're trying to get to here. Now, in order to prove these theorems, we need some tools, and we've been building them up. Actually, we've been building up basic useful definitions that are useful on their own, but there are two sort of side quests that we have to go on before we can go there. So right now we're going to do this one, theorem 9.19, which I don't really know a name for that one, but I'm just going to call it theorem 9.19. And then later on, probably next time, we will go do the contraction mapping theorem. Then we will be equipped to do the main quest of the course, which is these two theorems. And I think we will actually get done with these sooner than I anticipated. So we might have a lot of time after we're finished to do other things, which are yet to be determined. So here's the theorem statement, theorem 9.19. It's our usual setup, except we're going to assume that the domain E of F is not only an open set, but a convex set. So I don't know if you've seen the definition of that, but let's discuss that in a moment. And also, we're going to assume F is differentiable on E. Now, I don't think we've had any theorems so far where we assume something like that the function is differentiable not just at a point, but on the entire domain. So you always get interesting things when this happens. So what I mean is all our previous theorems were like theorems about a point, right? You can apply it to F being differentiable on all of E, but then you would be applying it to each point individually. Now we're going to get a theorem that really, since it makes this assumption, differentiability on E, must somehow require differentiability on all of E. So it's going to give some global kind of result. All right, so about convex, what does that mean? And by the way, I haven't stated, there's more to the theorem. I haven't stated the conclusion, but I just want to clarify what convex means. So a convex set is one for which the line segment joining any 2 points in the set is fully inside the set. So convex here means for all PQ in E, the line segment from P to Q is inside E. Okay, so like in the plane, this would not be convex because here are 2 points, and if you draw a line segment, it's not fully inside. You see it comes out. But, a ball is convex. A star is convex. Sorry, a star is not convex. If you just make a star shape like that, if you take 2 points like there and there, then the line segment joining them exits. But a ball is convex. If you take any 2 points inside a ball, you can show that the line segment between them stays inside the ball. And a lot of things are convex. So you'll see where we need that in the theorem. Now, the next assumption is that f prime is bounded. So what does it mean to say f prime is bounded? Well, f prime, which exists, we're assuming f is differentiable on E, f prime is going to be a map E to this metric space of linear maps from Rn to Rn. So if I'm going to talk about this being bounded, I must be talking about the norm on this, or the metric on this set. So I'm going to use the norm, and bounded means there's some m so that this is true. Okay, so that's going to be our assumption in the theorem. Assume there's some m, I guess it'll have to be greater than or equal to 0, so that if I take the norm of this linear map, then that's less than or equal to m for all x in E. All right. Then, the conclusion of the theorem, so under all these assumptions, then, for any pair of points, A, B, and E, the distance between FB and FA can be no more than m times the distance between B and A. So sometimes this condition is called Lipschitz continuity. So you can think of theorem 9.19 as saying if you've got a differentiable function and the derivative is bounded, then the function is Lipschitz continuous. So this kind of Lipschitz continuity. So the existence of an m that makes this true is what it means to say f is Lipschitz continuous. And hopefully it makes some intuitive sense that that you might get something like this if you assume the derivative is bounded. So this is kind of a measure of the size of the linear map, right? So it tells you how much at most a linear map can scale vectors by, right? And we're saying that that's bounded. So not scale vectors, but this number tells you at most sort of how much a linear map can lengthen vectors by what factor it can lengthen a vector. And so that's bounded. So that's telling you that the derivative of f at every point, in every direction, can at most lengthen vectors by so much. So changes in f can only be so drastic given particular given changes to the input. So if you have kind of E here, and you take 2 points A and B, then f can only change its value so much from A to B. And it's limited by both m and the distance between A and B. It kind of reminds me of some mean value theorem type results, or some of the exercises that you have to do right after you learn about the mean value theorem. And it's tempting to try to use the mean value theorem to do this, but it's not immediately clear how you would. The mean value theorem is about functions with real output and functions of a real variable. And here we have neither of those things. We're talking about a function of an n-tuple valued variable with m-tuple output. Okay, so let's begin the proof. So let's start by assuming the hypotheses and fix some arbitrary points A and B in the domain E. Okay, so here's the picture that I'm going to keep in my head as I'm doing this. I've got E, A, and B, and I'm trying to show that the change in the values of f from A to B, the distance between FA and FB, is bounded above by this thing. So I cannot apply the mean value theorem for the two reasons I described. One of those issues can be remedied. I can focus on a function of just one variable if I focus on the line segment joining A and B. So let's focus on that line segment. And let's call that gamma. So specifically what I mean is gamma will be a path inside E. Which starts at A and ends at B. So its value at t will be 1 minus t A plus t B. So here A and B are these vectors, they're n tuples, and these are scalars. And I'm guaranteed that when I write down this path, it does live inside E, it does have its output inside E, thanks to the fact that E is convex. So that's where the convexity is used. So the fact that gamma is in E means I'm allowed to look at this composition, f of gamma of t. So if I compose like that, then f composed with gamma, that's going to be a map from 0, 1 into Rm, which is where f takes its outputs. Now, I think it's tempting to try to apply the mean value theorem to f composed with gamma, but again, we still cannot really, because even though now it's a function of one variable, the outputs are in Rm, and the mean value theorem applies to functions with real output. But anyway, let's just define this to be g, and then let's express in terms of g what we know about the bound on the derivative of f. So let's just see what we know about g. So you can probably guess that we're going to use the chain rule, since g is this composition. And there's one slight issue. It's just a technicality, I guess, that with the setup in Rudin, with all of our definitions, in order to take derivatives, like if I want to take the derivative of gamma, the domain here has to be an open set. So really, maybe this should be minus delta comma 1 plus delta. Maybe I should grow it a little bit for some very small delta. But I'm not going to worry too much about that technicality. It's possible to do it. That's what matters. It's possible to grow this and make sure it's an open set. We're really only going to care about what's happening between 0 and 1. So I say it's possible because, if you extend this by a small enough amount here and here, you should stay inside E, since E is open, right? There are some balls around A and B that stay inside E. So let me leave that technicality aside, and let's just be okay with this, knowing that we could expand it a little bit and make it an open set if that's something we want to insist on. Okay, back to the main point here. Let's see what we know about the derivative of g. So to talk about the derivative of g, I'll have to know about the derivative of gamma. And let me rewrite gamma a little bit. You can rewrite this as a plus t times b minus a. And so this is exactly like the way we wrote linear paths in the previous lecture, and we verified directly that when you do this, we found exactly what we verified, that gamma is differentiable, and we wrote down the derivative explicitly. So from lecture 2, we know gamma is differentiable, and gamma prime t, which by the way is a function from let me write it like this. Gamma prime will be a function from 0, 1 to L, R, Rn, and it will be given by gamma prime t of h equals h times the vector b minus a, the displacement vector from a to b. So, in other words, b minus a is the velocity vector for the linear path gamma, and that's not surprising when you look at how it's defined. Okay, so now we can apply the chain rule. G is a composition of something that's differentiable, and we checked that in lecture 2, and F, which we assume is differentiable on all of its domain. So let's do this. Now by the chain rule, G prime of t, so let me just write down the type of thing that G prime will be. G prime will be from the domain of G to linear maps from R to R M here. And G prime t will be F prime of gamma of t composed with gamma prime of t. And so, actually let me feed in an h here so that I'm working with real numbers and not linear maps. So here of h. And so I'm looking at f prime of gamma of t of h times gamma prime of t, or sorry. This is nonsense. I'm looking at this linear map applied to another linear map applied to h. Like that. Now, the point of this was to figure out, to learn something about the derivative of g using what we know about the derivative of f. Namely, we know about the derivative of f that it is bounded. And this is the bound m here. So I want to use that and figure out what that tells me about g. So to get that bound into the picture, I need to put norms here. So let me do that. I think things are getting cluttered. Let me just use green. Okay, this is now less than or equal to the norm of this linear map times the norm of the vector that it's getting applied to. Don't read too much into what's green and what's white. I didn't put any logic into that. All right. And this, we know what this is, the derivative of gamma at t at h. That was b minus a. B minus a times h, right? Or I think it would be more natural to write h times b minus a, scalar times vector. And that's less than or equal to, so now I can use the bound I have on the derivative of f, m times, and let me write it like this, b minus a norm times the norm of a, the absolute value of the real number h. So here h is a real number because, you know, these are linear maps from R. Okay, great. So now I've got I've interpreted the bound on the derivative of f and reframed it into some information about g. And this is good, because G is something I can more readily apply the mean value theorem to, although still not directly. So I just want to take a moment now to maybe try to get some intuitive feel for what we just got. So one way to express what I just got, this thing with the h's in it, so right now this is like for all h in R, this entire thing. But one way to express it is, it's saying that the norm of G prime T, the norm of this linear map, is like that for all T. That's what it's saying. So this is what we achieved. Now, this norm of this linear map, this is the speed of G. So there's a nice picture to go with what's happening here. So since I keep scrolling the screen here, let me remind you the type of thing G is. It's this. And so, you know, G of 0 starts somewhere, and it's a path inside Rm. So let's pretend that we're looking in Rm here, and then it ends at G of 1. So this is telling us that the speed of the path G is bounded above by this number. So this is just some fixed real number in our context here. So we have a path G, and the path is allowed to run for 1 unit of time, from time equals 0 to time equals 1, and its speed is bounded above by this. Well, if you're only allowed to run from time equals 0 to time equals 1, and your speed can at most be this, then you can only run so far, right? G can only go so far away from G of 0. So, in fact, probably what you would predict is the furthest G could go away from G of 0 is like how far it would go if it went in a straight line at this speed. So it seems like wherever G of 0 is, there's like a ball that contains how far it could go in 1 second, given the bound on the speed. So that's the idea. We're going to try to turn that idea into a logical argument, and hopefully the bound on how far G can go, given the definition of G, F composed with gamma, that should give us what we want, which is a bound on how much F can change as you go from A to B. Okay, so how to turn this into an argument? You've got G of 0 somewhere, G of 1, and there's a displacement vector from G of 0 to G of 1. So that's G1 minus G0, this displacement vector. And we cannot apply the mean value theorem to G because it's not a real valued function. However, if we dot product G with various vectors, then that's ways to get real. If we dot product the output of G with a fixed vector, then that's a way to get a real valued function. So the trick ends up being to dot product with this displacement vector, which is the direction that G would have to travel in order to cover the most distance that it possibly could. So let's take G of t dot G of 1 minus G of 0. And let's call that a new function, phi of t. So that's going to be our definition of phi of t. So that means phi is this kind of function. That's something we can apply the mean value theorem to. Okay, if it's differentiable. So we know G is differentiable. We knew that from the chain rule, and we worked with the derivative even here. But is phi differentiable? Well, it must be. It's not such a complicated function, right? Let's write out what phi is kind of more explicitly. So phi of t is the sum from I equals 1 to I equals m of the ith component of g of t times the ith component of this displacement vector. That's how dot products work, right? So then phi of t is a sum of functions. It's a sum of these mappings from t to these things. And so if each one of these is differentiable, then phi is differentiable. So here's our textbook by Abbott, our previous textbook from 118b and 118a, and we are just using the algebraic differentiability theorem, this fact. Okay, so the next question, are these individual functions differentiable functions of t? Yes, so this is just a constant times this function of t. So as long as this function of t is differentiable, yeah, we're good. Well, this thing, so again, that's again due to the algebraic differentiability theorem. Take a function multiplied by a constant, that doesn't harm the differentiability. But then this thing is going to be, so this is like, the derivative of this would be what we would refer to as sort of d1 g at t, one of the partials, except it's not really a partial, I guess. You wouldn't call it a partial since it's a function of one variable, but it does follow our definitions to call this capital D sub 1 g of t. And since g is differentiable, and we just proved that if a function is differentiable, then all of its partials exist, we know that this function is differentiable, its partial exists. Something's wrong with the way I'm writing it. I'm not saying this is this, I'm saying this has derivative this. Okay, so that's why phi is differentiable. It's a sum of differentiables, and these individual ones are differentiable because we have already connected differentiability of a function to the differentiability of the partials. And we said when the function is differentiable, the partials are. Okay, and in fact we can say exactly what the derivative is. So d dt of phi of t is going to be, then I just take the derivative here, so it's just dgi dt times g1 minus g0 I. Which, another way of writing that, like I was saying, is to think of it using that notation, d1 gi t g1 minus g0 I. And by the theorem that we just got done proving, theorem 9.17, we know that these are the components of g prime of t these are the components of g prime of t of 1. So then this sum is a dot product, g prime of t of 1, with this vector. So the 1 is coming from the fact that 1 is the one standard basis vector for the one-dimensional vector space R. All right, so there's the derivative of phi. That's pretty nice. Now let's think about the mean value theorem. So let's apply the mean value theorem to phi. We know phi is differentiable, and here's its derivative. So by the mean value theorem, there is some t in 0, 1, so that phi of 1 minus phi of 0 equals phi prime of t times 1 minus 0. So this is what the mean value theorem gives us. Okay, and phi prime of t we just saw is this thing. I'm sorry, let me revise that. I'm mixing up old and new notation, and it's going to get incredibly confusing. So I should not call that phi prime of t. I should call it d phi dt at a particular t. Let me call it t naught. So there's some t naught so that this is true. And here I should put t naught. Hi, it's me from the future. So what happened is my microphone ran out of battery. And don't ask me why I'm using a microphone that requires a battery, but I just had to use what I had for reasonable sound recording. Anyway, the battery ran out and I lost the audio on the rest of the recording. So now I'm going to record new audio on top of it, and so it's going to look weird because the audio does not match up with the video since it's recorded after the video was recorded. Okay, so let's get back to it. So here I'm going to write out what phi is using the definition of phi. So I'm scrolling back up to find the definition. Looks like I'm confused for a little while, and there it is. So phi is gt dot g1 minus g0. So that means phi 1 minus phi 0 is going to be g1 dot g1 minus g0 minus g0 dot g1 minus g0. Which can be rewritten like this. In other words, we have the squared norm of g1 minus g0. Okay, I don't know what past me was rambling about at that point, but I think the next step is just to write things out. Right, so we have that we have a bound on the derivative of g, so we're going to go back and use that. And it looks like what I'm gesturing there is the Cauchy-Schwarz inequality. So to make use of the bound on the derivative of g, we need a bound on the dot product. And the Cauchy-Schwarz inequality is telling us that the dot product can be the biggest only when the vectors are lined up, in which case that's the size of the dot product there. And I can tell you that past me made a typo here, and there should have been a 1 after the g prime of t naught. All right, so here I'm writing out what we've got so far. And we're noticing that we can divide by this thing that I'm underlining here, as long as it's not 0. So if it were 0, we would actually be finished. And here I'm going to scroll up and show you why. If G0 equals G1, then if you look here at the definition of G, that's just telling us that f of gamma of 0 equals f of gamma of 1, meaning f of A equals f of B. And if you look here, that means we're done, right? If f of A equals f of B, well, yeah, 0 is certainly less than or equal to that non-negative thing. All right, so let's just get that case out of the way. If g of 0 equals g of 1, then we are done. And otherwise, we get this from dividing out g of 1 minus g of 0, and I look puzzled there because I think I just found the typo that I mentioned. So yeah, there should have been a 1 there. And I mean, it still works without the 1, I guess, because technically the norm of g prime t naught is the norm of g prime t naught of 1, just in this situation. But I had it with the 1 there, so I should be consistent. All right, and then notice that that thing on the left-hand side, that's f of b minus f of a. That's just because g is f composed with gamma. And then I'm going to go up and find the bound that I got on the derivative of g, which was way up there, right there. G prime of t is always bounded above by mb minus a. So if I plug in 1, you know, the upper bound is still m times the distance between a and b. So there we are. And that finishes the proof of theorem 9.19. And here I'm just reminding you what the theorem says. It says that if you have a function that's differentiable on an open convex set, and the derivative is bounded, then the function is Lipschitz continuous. Or another way of saying it is, if there's a bound on the derivative and the bound is m, then the difference between f of a and f of b here, the distance between f of a and f of b cannot, the jump from f of a to f of b cannot be more than m per jump from a to b. And finally, I also wanted to mention a corollary in Rudin, just picking it out of Rudin, and we might as well say it because it's easy now. If you have this setup, you have a differentiable function on an open convex set, and you have it with m equals 0, so say you know the derivative is 0 on the entire open convex set, then you can conclude that the function is constant. So if this m here is 0, man, I don't know why it takes me so long to say those things. All right, if the m there is 0, then we have the result there with the m being 0, so that just tells you f of a equals f of b on the entire set E.